Okay, so I'll be talking about the various options for equilibrium calculations in the TRANSP code. Um, as an overview, TRANSP uses a axisymmetric MHD equilibrium with nested flux surfaces within the separate bricks. Um, and the equilibrium geometry that it maintains, it evolves on a slower time scale than what the profiles are evolving on. So the profiles are on whatever the nested flux surfaces are, and those evolve over a longer time scale, the equilibrium will change. And in TRANSP, the equilibrium options are selected by variables in the name list in the tr.dat file. So the master variable to choose which equilibrium option using is called LebGeo, and there are three supported options for that right now. LebGeo equals 8, which will read the equilibrium from user-provided U files and just use those. 11, which uses the fixed boundary equilibrium solver TEQ, and 12, which uses a free boundary equilibrium solver iSolver, and I'll be talking about all of those options. Fourth option is under development using the eFit AI equilibrium solver. So first, the simplest option is using U files to specify the equilibrium. So in this case, it's read from user-provided files in the U files format, and it could be interpolated in time. Typically, these are moment expansions of the flux surfaces. They could also be R and Z specification. Either of those are generated by the Scrunch2 utility, which is a part of the TRANSP library, and that's produced along with the Q profile and pressure profile from eFit data from an MDS Plus database. So when TRANSP is using this U files method, it does not perform any calculations to ensure physical consistency of the equilibrium evolution. It's just relying on the data that's provided to it. There's also more recently an option to read this data from an IMAS equilibrium IDS instead of these text files. And all of the reading and interpolation in time is done during pre-processing step with the TR-DAT utility, and the results are stored in a netcdf unified physics file, and TRANSP uses that during the main run. Another option in U-files mode is to provide the poloidal flux as a function of R and Z in time on a rectangular mesh via brief psi and x psi U-files. If this is done, then additional analysis is done in it to find X points, magnetic axis, and a bounding point using part of the iSolver library. And this makes some additional plots are available. And if in addition you set the nameless variable NL psi RZ flux to true, then those flux surfaces will be used in place of those that would be read from the U file. So you can use psi instead of that. And then there are some submodes if you're doing this and psi RZ mode. So the default is 102, which uses the TRANSP Q profile along with psi to map the geometry to the native minor radius coordinate, which is square root of toroidal flux. There's also minus 102, which uses the input Q profile to do that. Then 103 uses the TRANSP RB toroidal profile along with psi to infer Q to be used in the mapping, and then minus 103 uses the input G and Q profiles. And that's about all I have to say about the U files option. The other options are a little more involved. So the next one is LebGeo equals 11, which is the TEQ fixed boundary equilibrium. This one uses a version of the TEQ code from Livermore, which originally came from the Corsica code to advance the plasma geometry. The way this code works is that you give it pressure and Q profiles, vacuum RB toroidal as a boundary condition, and it iteratively adjusts the edge Q profile to match the total plasma current. So because this is an iterative algorithm, it works better with a warm start. So you give it an initial inverse equilibrium that it then evolves to match those profiles. So the TEQ option requires the existence of an already calculated inverse equilibrium for whatever your target device is. So if you have a new device, you have to right now request that a TRANSP developer generate a new inverse equilibrium file for it, which we typically do starting with an existing equilibrium for a device of similar size. So some of the options, if you're using the TEQ solver, you can set the number of radial points and number of poloidal points with NTEQ and rho and NTEQ and theta to set the resolution of the calculation, and given the default values of those here. Then the mode for TEQ is set by NTEQ underscore mode, which determines the free parameters that are matched in the Grad-Shafarov solution. So you can match the surface average J dot B in the plasma current, the Q profile in the plasma current, the vacuum RB toroidal in the plasma current, Q and the vacuum RB toroidal. The default is to match Q and edge F with a loop that also matches the plasma current. And finally, option 6, surface average J dot B and edge F. There's also smoothing that we recommend be applied to the TRANSP data that's provided to TEQ, which is can be normalized to the number of zones, as is the default. The default value is minus 1.5. There's extra smoothing that can be applied near the axis, and it can also dehollow the pressure profile near the axis before smoothing if that seems to be necessary. The default of that is 0.05. And you can set the maximum permitted Grad-Shafarov error to consider a TEQ solution successful, and the default for that is 0.3. Okay, most of the rest of my talk will be about iSolver, the free boundary solver, which has the most options. So that's the LevGL equals 12 option. And this, so iSolver is adapted from code written by John Menard, and it attempts to converge to a free boundary equilibrium solution out to the limiter or beyond, consistent with the known set of axisymmetric colloidal field coils and passive conductors and ohmic coils surrounding the plasma. And there are two main modes for iSolver: least squares mode, which is the default. It adjusts the coil currents to match a known plasma shape that's provided by the user. And then in circuit mode, it uses supplied coil currents to constrain the plasma geometry. And both of these modes require pre-existing files with detailed coil data for the target device that are then at build time. These are used to generate data used by iSolver in the solution, and developers can generate files for new devices on request. But as I'll talk about later, an option to generate these as a pre-processing step based on IMAS data has recently been added for testing. And there are a lot of user adjustable options for using iSolver and TRANSP. So I'll get into those next. So in the least squares mode, which is the default, you just selected by leaving the FB underscore names variable undefined. The poloidal field coil currents are adjusted, as I said, using the least squares minimization to best match the plasma boundary provided in the input equilibrium files, which again would come from U files or possibly an IMAS database. And in this case, you can either leave the coil current values unconstrained, or you can put a weight on the errors from matching experimental values that can be provided in a PFC-U file. And vessel currents are not available in least squares mode. So the EQ cur weight, EQ x weight, and EQ ref weight are nameless options that can set relative weightings on errors in the current matching X points and boundary in this mode. And typically the computed coil currents in least squares mode are not that well correlated with the measured values, but you can constrain them to a measured value with the PFC underscore sigma variable, which is a vector, is one for each coil index, and set that to -1. And that can be especially useful if you want the ohmic coil, for example, current to match the experiment. Okay. Now, to really do a free boundary calculation, you want to use iSolver in circuit equation mode, which you activate by setting a list of feedback circuits with the FB underscore names nameless variable. And in this mode, there are still target poloidal field coil currents that can be taken from the PFC-U file. or they can be calculated just in time, as I'll talk about in a following slide, to drive the coil circuits and vessel currents. And the feedback circuits modify the coil currents and can to position the plasma and drive the OH coils. So there is a text file that's normally in the TRANSP directory of feedback circuits for each device. So typical feedback circuits name would be like IHAR for current constraint on horizontal control, or VVER would be voltage constraint for vertical control. IOH would be constraint for ohmic, and those would be the names that would go in your list of FB underscore names to activate this mode. And in this case, if you have a prescribed U-file plasma boundary equilibrium, that's still used in this mode to guide the plasma positioning, but the plasma can move around based on the coil and conductor currents. Some options that can be used in this mode to assist in convergence. Sometimes the plasma boundary computed by this doesn't match the supplied equilibrium very well. So if that's the case, you can set the X boundary check variable to 0 to disable checking of that match and turn off errors or warnings about that. There's also NISO underscore NJ pre, which you can set to -4 to add a 4-point iteration filter to J5, which is helpful at high beta. So what I've described is the circuit equation mode with provided currents, but if you set the variable NPFC underscore JIT to a number greater than 0, you can get just-in-time currents instead, in which case, if you don't have coil currents available from measurements, you can generate the circuit currents at each geometry time step in order to calculate the equilibrium. And this mode uses least squares optimization again with the X-point boundary and current constraints to help find those coil currents. So the options for this are NPFC JIT equals 1, which generates the currents using currents provided in a PFC file or provided in a nameless variable, PFC underscore cur. Also uses PFC underscore sigma, which is a weighting on the error, and PFC underscore JIT voltage. And as constraints. If you set it equal to 2, it does that, but it uses the PFC sigma only for the first time step, and then there's a formula PFC JIT sigma for as a function of the coil index plus the current times another nameless variable XISO def JIT sigma pcur for subsequent time steps. And if you set it NPFC JIT to 3, it uses that last formula for all time steps, including the first time step. Some other options for the just-in-time coil current mode are XISO JIT relax, which relaxes with the least square solution to the just-in-time currents over the interval in seconds. Then you can provide a default constraint for coils that don't have individual constraints through the XISO def JIT sigma variable. And then there's the XISO JIT sigma pcur variable, as mentioned in that formula above, that scales the just-in-time error constraints by that factor of the plasma current. Another option in iSolver is the flux diffusion option, which is activated by setting nameless variable NL ISO diff to true. So if this is done, then iSolver can evolve the Q profile self-consistently with the equilibrium over the geometry time step by diffusing a toroidal flux profile on the colloidal flux grid. And if this is selected, it will override the normal transpolloidal field diffusion equation that's activated with the NLM diff equals true option, if this NL ISO diff is set to true. Now, flux diffusion requires the rate of change of colloidal flux at the magnetic axis to satisfy this equation, d psi 0 dt is eta j phi. But there's no condition in the code to constrain psi 0 based on the coil currents. So the code variables psi 0 and psi 0 diff are distinct. They're not necessarily going to be the same. And the flux diffusion works in both least squares mode and circuit equation mode. And in least squares mode, you can use the total plasma current or the surface voltage, but not both, to set the boundary condition for flux diffusion. So NLP cur equals true uses the plasma current, and NLV SIR equals true uses the surface voltage. You can do the same thing in circuit equation mode, but there, if you use the ohmic coil feedback circuit, you can help minimize the error, the difference between size 0 and size 0 diff. iSolver also can take into account the effective plasma rotation on the equilibrium, and that comes in through the effective pressure. So the rotational energy density that gets fed into the equilibrium solvers has components from the thermal plasma, the fast ions, and rotational component. And in iSolver, you can substitute the rotation of each individual ion species instead of the bulk plasma rotation. And that's determined by the choice of this NISO-ROT nameless variable. So if you set that to -1, it just uses which is the default, it just uses the input MHD pressure. If you set it to 0, you get rotation modified pressure, assuming 0 rotation. If you set it to 1, it does the pressure with all speeds using the bulk rotation. And finally, if you set it to 2, you get rotation modified pressure using the separate rotation profile for each species. If you are using multi-species rotation, then there's a sub option, NISO-ROT _spec_OMG. So you can set that to ±2 to do N class so if it's -2, it runs N class to find the species rotation using the existing radioelectric field, using all species. Set it to -1, it uses the existing radioelectric field, but the impurities are reduced to a tokamackium equivalent. Set it to 0 to use omega for all species, which is equivalent to NISO-ROT = 1. NISO-ROT spec OMG = 1 runs N class with the radioelectric field loop with impurities reduced, and finally 2 N class run with the radioelectric field loop with all species. And also when you're using rotation, the density is no longer a flux function. Okay, so those are the major different options for iSolver. Some of the outputs from iSolver that you may be interested in for plotting purposes, CC _ the coil name will give you the total poloidal current in the coil, which is the number of turns in the coil times the circuit current in that coil. Circuit current given by KK name. You can get the poloidal current for the coil as input from the PF name. Then you can do multiplots of these coil curves will give you the poloidal current in each of the coils. SIR curves gives you the circuit currents for each of the coils. And PF curves give you the coil currents from the U file. And there are also some options that can plot these against each other to look at the errors between the calculated and provided currents. You can also, if you set the N-SIRZ out nameless variable to 1, which it is set by default, then the code will also output the poloidal flux on an RZ grid, which can be plotted to show the shape of the equilibrium. Okay, so that is pretty much what I wanted to say about iSolver, except that a new utility that has just been introduced to the testing branch of TRANSP this week is the runtime make eqtalk option, which can generate iSolver device files at the beginning of a TRANSP run instead of during the build phase. So in the build phase, you would generate a static database of iSolver device files. But with this new option, you can invoke make eqtalk at runtime to generate a device file based on coil data that's read from an IMAS database. So the PF active and PF passive IDSs respectively contain information about the active poloidal field coils and the passive conductors in the vessel. That data is read by this utility. Then there are iSolver specific options that need to be set for make eqtalk, including the feedback circuit specifications. And for this option, you have to provide those in an XML string that goes in the code/parameters field of the PF active IDS. And I can provide examples of how to do that on request. So the syntax in this case would be make equitoc IDS and then device name, shot number, run ID. You can specify whether the input IMAS database is in HDF5, MDS plus, or ASCII format. The default is HDF5, and you can specify an output path for the iSolver files that will be generated. The default is the current directory. Okay, so that's basically what I had to say. To summarize, the TRANSP code provides a number of options for advancing the magnetic geometry during a calculation, and more are being developed. You can use reconstructed experimental equilibria without recalculating using the LevGeo equals 8 option. For fixed boundary calculations, you can choose LevGeo equals 11 to use the TEQ equilibrium solver. For free boundary calculations, we use iSolver with the LevGeo equals 12. The default for that is least squares mode. Circuit equation mode, though, evolves the equilibrium shape based on the coil currents. And if you're looking for more flexibility in device specification, you're invited to try the new runtime make equitoc utility. And more documentation on TRANSP equilibrium solver options can be found at the URL below. Okay, that's it. Thanks.